Hello, this is Sanjay from CSIT branch, and today my applied physics AAT Tech Talk topic is mid-infrared tunable quantum cascade lasers for gas sensing applications. Introduction. Semiconductor lasers are familiar to most people as light sources in laser pointers, laser printers or CD players, as well as optical communications. In the later application, they have reached a very high standard of sophistication with ultra-fine control of wavelength, typically from 1.3 to 1.5 line width and output power. They are mostly built from in p-based semiconductor heterostructure materials. They semiconductor lasers that are available. While optical data storage evolves towards blue lasers and optical communications around near infrared wavelengths, another wavelength range, the mid-infrared, ranging from -3.5 to 12 picometers, is attracting a lot of attention. Most traces gases of important from byproducts of burning fossil fuels to constituents of human breath have telltale absorption features in this wavelength range, known as the molecular fingerprint region of the spectrum, as a result of molecular rotational vibrational transitions. Quantum cascade lasers QC-DFB lasers have evolved very rapidly and have already shown great promise in many different gas sensing applications. Light is generated when an electron makes a transition from an upper energy state to lower energy state, emitting a photon of exactly the energy difference of the two states. In QC lasers, these energy levels, the upper and the lower laser level, are produced in the conduction band of a multiple quantum well structure. These layers in the wells are alternated with thin layers of all-in-as barriers. These layers are so thin that the allowed energy levels of the electrons are noticeably separated, so that their separation exceeds the natural broadening of the individual states. Using the same approach demonstrated from the 9.5 picometer wavelength laser, also called the 3-well vertical active region, Q lasers with wavelength as short as 3.5 picometer and up to 13 picometer have been demonstrated. Figure shows a transmission electron microscopic image of such a laser imitating 5.2 picometer. Many different approaches to various types of active regions have been used as well, containing 1, 2, 3, 4 or more quantum wells. QC lasers are routinely operated up to room temperature and above in pulse mode with 50 ns pulse width and less than 100 kTL repetition rate in the wavelength range from -4 to 11.5 picometer. Record peak power levels of 0.5 were achieved around the 8 picometer wavelength, either by employing a very high number of stages or by using large aperture devices geometers at lower temperature, example liquid nitrogen temperature. Peak power levels are higher, close to 1.5 volts. Continuous waves operation is presently limited to temperatures below 175 Kelvin 1241. However, at LN2 temperature, maximum power levels of 200 per facet have been measured at 5 and 8 kilometer wavelengths. Single mode tunable OC distributed feedback laser. Typically, QC lasers are processed as deep H rigid waveguide lasers several micrometers wide and 1.3 mm long, while the narrow ridge provides good current confinement and also lateral optical confinement. The extended length of the device is needed to reduce the effect of the outcoupling losses from the cleaved laser facets that serve as the cavity mirrors. With only -30% reflection, the alternative approach of depositing a high reflection coating onto at least one facet is more difficult for the longer wavelengths and sometimes contents with unwanted absorptions in the coating material. The longer cavity leads to a spacing of the Fabry-Perot modes that is small for a long laser compared to the width of the gain spectrum. This is responsible for the lasers operating in the multiple modes under usual conditions, certainly in pulsed between as CW at higher current levels. Most traces gases of important characteristics absorption features in the mid-infrared between 3 and 12 μm wavelengths. This characteristic QC laser waveguide 1251 provides several opportunities to produce aggregating modulations strong enough to provide the necessary wavelength selective feedback. In the first type, the grating is etched into the surface of the waveguide with 3 consecutives shows a partial photograph of such device. First, the waveguide loss in the position of the grating grooves is higher than in the position of the grating ridges. The, the unetched position of the grating leading to the loss modulation of the waveguide. Second, the metal layer in the grating grooves now closer to the lower doped section of the waveguide pulls the mode towards itself. As the mode is pulled into the top cladding layer, its effective refractive index, defined as the average refractive index of the various waveguide layers weighted by their overlap with the optical mode changes. Depending on the actual etch depth compared to the thickness of the cladding layer, one component of waveguide modulation may win over TT. Other ones, all our gratings were fabricated by optical contact lithography and wet chemical etcher in aged HBr HNO3 HZO. The obtained etch depth of practical reasons limited. The single mode emission wavelength is very close to the Bragg wavelength, where NFF is the effective refractive index of the waveguide and A is the grafting period. Grafting periods will vary from 800 nm from H5 emissive wavelength to 1.5 picometers. Gas sensing applications using AC lasers. Figure 4a shows several single mode tuning ranges of OU QCDFB lasers operated in pulse mode. Figure 4b shows the transmission of several hundred meters of standard atmosphere at sea level. Two large regions of good transparency are found around 5 picometers from 7.5 to 13 FM. The HV are called as atmospheric windows. Furthermore, most trace gases of importance have characteristic absorption features in the mid-infrared between 3 to 17 FM wavelengths. As discussed earlier, QC-DFB lasers can be designed to emit any wavelengths in this wavelength range. Therefore, it was straightforward to examine the lasers' potential in demanding gas sensing applications. To that aim, many fruitful collaborations with expert spectroscopists were established. Some of these results are presented in the following. Whitaker et al. From Stevens Institute of Technology, New Jersey, used to pulse QC-DFB lasers with a top grating at near-room temperature conditions to measure the mid-infrared absorption spectra of NZO and Cl14 diluted in NZ. This employed a measurement technique known as wavelength modulation spectroscopy. The noise equivalent sensitivity limit of the measurement was 50 ppm. Finally, Webster and co-workers in 1161 at JPL, California Institute of Technology conducted measurements of the concentration of Cl, LQ, NZO in the Earth's atmosphere from ground level to the stratosphere. Closer to wavelength modulation technique, the laser is 1 NZ DVAR as was placed board into high aptitude airplane. He surrounded air was sucked into a multiple pass gas cell aboard the plane as the plane made 8 hours long flights to map the atmosphere from the trace gases. The noise equivalent sensitivity limit was 2 pBB. Several more projects are underway to either demonstrate the QC-DFB qualification of the demanding gas sensing application. Despite being quite recent inventions, QC and QC-DFB lasers have already achieved a high level of maturity. The future. Despite being quite recent innovations, QC and QC-DFB lasers have already achieved a high level of maturity, demonstrated by the many laboratories and research groups who study, fabricate, or use the lasers. Still, some questions remain unsolved thus far. First of all, for QC-DFB lasers, there is a quest for the higher CW operating temperatures. This has been made impossible by the large dissipate power and the limit options for the efficient thermal management of the large devices. Other fields research of lasers fabricated from multiple wavelengths which would emit correspondingly multiple single modes, and the extension of the accessible wavelength range into the near infrared as well as into the far infrared. Finally, the wide commercial availability of the lasers would be desirable. And these are some of the references of my AAT Tech Talk topic. Thank you.